Folks, welcome to our help video on the Chromatography Lab 2-6. The answer key does have answers to the questions. I'm not going to go over every one of the questions because most of this first page, numbers 1 through 5, the answers and explanations are on there, and I just don't want to I don't want to read those to you. But carefully look over those different sections. And if you have questions and do not understand questions 1 through 5, please just email me and we can discuss it. We can set up a Zoom or special office hours or whatever to go over anything on 1 through 5 that might be causing confusion. Question 6 came from the video you watched. You were only supposed to watch the first minute of the video, and these are the 6 factors that are involved on how chromatography works to separate molecules. Those are the 6 factors. Then we get to the actual lab. The part that you had to do something on were to fill in the numbers for the calculations. For this part, every person might have different answers to these because you may have been asked to identify a different band. The way you can tell if you did it right was by looking to see if when you answered on the simulation there was a check mark. If there was a check mark there, if a blue check mark popped up like you saw in the lab introduction, the pre-lab videos, if there was a check mark there, it meant you did it right. If not, it would have told you you did it wrong. And if you're having trouble calculating RF values, again, what you needed to do was measure how far the spot went up. And generally, you look somewhere in the middle. So this spot went to about here. This spot went to about here. This spot went to about here. That one there, so forth and so on. That's the first number. That's the number that goes on the top, or the numerator, is how far the pigment made it. The second number is how far the solvent made it, and the solvent line is right there. And in all the different portions of the experiments on trial 1, 2, 3, the solvent made it to 6.2. On number 4, the solvent looks like it only went up to 5 centimeters or so. But that would be the number that goes on the numerator, or the denominator, the number that's on the bottom. The number that's on the bottom is how far the solvent traveled, and that's the little gray line. How far the pigment traveled, you measure it to about the center of the pigment, and then you divide those two to get the RF value, the retention factor. And that retention factor, if you're thinking about, like, what do they mean by retention factor? It's really how well the paper's retaining the pigment, how hard it's holding on to it. And it's like comparing it to how far the solvent is able to pull it up. So it's a tug of war. It's a tug of war between the paper holding it and the solvent pulling it up the paper. Retention factor. All right. Everyone could have a different thing, different answers for those, and the simulation will tell you whether you had it correct. And then we get on to the conclusion. Be sure that you record your number here. You could take the quiz over if you wanted to, but that's just kind of checking the basics of your understanding, and you just click on the Viva Voce or Viva Voce, or however you say that. I don't know what even language that is. But put your score there, and then we get to the rest of the conclusion. And this is the first question, number 1 here. They're talking about there's an adage that likes dissolve likes, or likes attract likes. And this means molecules that are attracted to other molecules have similar bond types or intermolecular forces. And we mentioned those in our pre-lab discussion videos. What that means is some molecules have atoms on them where the atoms are not sharing the electrons equally, where one of the atoms is pulling harder on the electrons than the other atom. Whichever atom's pulling on the electrons more tightly actually will have those negative electrons around them a significant amount of the time, making that atom behave as though it is negative. It's not negative, it's just behaving like it's negative. The other atom that is having its electrons pulled away from it will be behaving like it's positive. That kind of covalent bond where they're not sharing equally makes the atoms act like they have little charges, which we call poles. It's called a polar bond. There's a negative and a positive polar bond on there. Partial charge. Molecules that have that force, that pull on them, will attract other molecules that have that pull on them. Other molecules have the atoms being held together by covalent bonds where they're sharing electrons, but those electrons are being shared equally. In other words, one of the atoms is not able to pull the electrons to it. There are no pulls. That molecule is said to be nonpolar. There will not be a pull on that molecule. So that molecule will attract other molecules that don't have pulls. Likes dissolve likes. Now our question here is asking which color or pigment has bonds, intermolecular forces, most like the paper. Likes dissolve likes. So they're really asking which one is most attracted to the paper, which of these colors. The answer is chlorophyll B, the dark green. How do we get that answer? Well, if we look up here, the dark green in trial 1, the dark green in trial 2, and the dark green in trial 3 does not go up the paper as far as the other colors. So that means that that color is the one that is most attracted to the paper. So they must have similar types of attractive intermolecular forces. It turns out that paper tends to have polar bonds. So in other words, in paper, the molecules that make up that paper are not sharing the electrons equally. So there are little pulls on the different atoms on the molecules of the paper. And those pulls on those molecules are able to pull on the pulls of a molecule. So the molecule that has polar type bonds must be the dark green, the chlorophyll B. Now they're asking us to look at trial 1 and 2. Which solvent was the chlorophyll B, the dark green, most attracted to? Which solvent was it most attracted to? When we go up here, which solvent was it most attracted to? Trial 1 had ether acetone as the solvent, or the mobile phase. Trial 2 had the isopropyl alcohol as the mobile phase. That's the stuff that was called mobile because the solvent is moving or is mobile up the paper. The one that the dark green is most attracted to would be the one that it went up the paper the furthest. So it must be the ether acetone. The dark green was more attracted to the ether acetone because it traveled up the paper with that solvent. And as we can see here in our answer, we have the ether acetone. We have the ether acetone. Question number 3, looking at the results of the first 3 experiments and assuming the other separation factors. Remember, there were 6 factors that they mentioned on that video. Which color or pigment is least attracted to the paper and most attracted to the solvent? Well, the one that's most attracted to the solvent will go up the paper the greatest distance. If it's more attracted to the paper than the solvent, then the paper will hold it. It won't get up very far. If it's more attracted to the solvent or the mobile phase, it will go mobile up the paper. So let's take a look and see which colors made it up the paper the furthest. Look here, it looks like the yellows are up there. We're looking at trials 1 through 3, not trial 4. We come down to our question, which one was that? That was the yellow-orange carotene. So, assuming that the solvent is not quite as polar as the paper or whatever, we would say the carotene would be more of a non-polar molecule than the dark green, which was held by the paper. If the paper has lots of pulls on it, it's a polar molecules, then the chlorophyll B is polar. This one must be more of the non-polar because it went up the salt with the solvent. We take a look at our next question. Looking at the results of trials 3 and 4, why do leaves turn colors in the fall? So we're now going up to 3 and 4. Here's 3 and 4 right here. This is trial 3. Those are the leaves in the spring and the summer, maple leaves. Here's trial 4, maple leaves in the autumn and winter. Why do they change colors? Well, we can see in the spring and the summer, there's lots of our greens. We have the light green chlorophyll A. We have the dark green chlorophyll B. When we look at the fall and winter, the light greens and dark greens are gone, and we are left with the yellows, oranges, and reds. There is no chlorophyll A and chlorophyll B in that leaf anymore. All right then, number 5, why are there no units for the RF value? Well, to get the RF value, you measured how far the spot traveled, or the pigment, or the color, or whatever. That went on top, and we measured it in centimeters. Then we looked to see how far the solvent traveled. How far did the solvent travel? We also measured that in centimeters. So we had a number with centimeters as a unit. On the top, we had a number with centimeters unit on the bottom. Those two units canceled out. So RF value is just the ratio of how far the color traveled, or the pigment, divided by how far the solvent traveled. The units cancel out. Which pigment on number 6 is not found in chlorophyll B, or which is not found in spinach but is in the maple leaves? Which one is not in the spinach but is in the maple leaves? So we come back up, we look through here. The maple leaves had the reds, the anthocyan. The spinach did not have those reds. The spinach did not have the reds. And if you saw that, it said NA. When you looked at the charts for those, it was NA, not applicable. There was no reds. There were no anthocyans in the spinach green. Will spinach then turn red in the fall? The answer is no. If it doesn't have any of the red pigment, it cannot turn red. So the reason you see reds, oranges, and yellows in the fall is because those leaves have those things. Whatever color a leaf turns in the fall is telling you which of the pigments are present in it. Now we go down to the Khan Academy. What is column chromatography useful for? It is used quite frequently for purifying drugs. Many drugs, when they produce drugs in the laboratory, they're very often a mixture of some different compounds in there, and they can use column chromatography to separate those mixtures. What's the stationary phase? That's the stuff that's not moving in there. The stationary phase is the stuff that you pack inside the column, such as the silica or whatever material you put inside that column. It does not move. What is the mobile phase? Well, they poured the solvent into the column, and the solvent ran through the column, through the stopcock, which is just a little valve, and into the catching flask. The mobile phase is the solvent. You were supposed to draw a sketch of it. Any sketch you draw would have been fine. The portion of the mixture, the blue, which can move easiest through the stationary media, will do what? It will move through the column and out the stopcock. So whatever can go through the stationary the best, whatever's not attracted to the stationary stuff, will move through it. And it'll go into the catch flask. The stuff that is attracted to the media that's in there, the stationary media, the stuff that's attracted to it by intermolecular forces or whatever, will not move through as well. It won't go with the solvent. So if it's attracted to the solvent, it will move through. If it's not attracted to the solvent, but it's attracted to the stuff inside here by the intermolecular forces, then it'll have trouble moving through. It will stay inside the column. Hopefully you have an understanding of how chromatography works. If you need help or have questions that were not answered in this video, do not hesitate to email me, come and see me, or by Zoom or whatever works best for you. Thank you very much. Submit that lab when you're done.